previously and at the school, I just would like to remind what the school and my lecture is dedicated to memories of Professor Sergei Zelitsinkevich, outstanding scientist and teacher of many of us, and good friend. And he provided really a great theoretical platform for modeling of atmospheric processes, especially within the boundary layer, which is extremely important for the studies what we are discussing today. My lecture was today and together with Alexander Mahura, focusing on seamless prediction from Earth system to integrated urban hydrometeorological climate and environmental systems. Yesterday, we already started discussing integrated modeling for atmospheric pollution processes. Today, we'll try to take a look on more broad aspects, and here some outline of the lecture is presented here. And I just would like to stress what I would like to say a few words about the World Meteorological Organization and main priorities globally in these directions, what now we are developing. And in the first part, I would like to say about the Earth system prediction with seamless approach, and specifically focusing on coupled chemistry meteorology modeling. And here you can see main bullet points, but I'll focus on 1 and 2 within the part 1, because the following bullet points yesterday we already discussed. And in the second part, if you'll have enough time, I would like to focus on urban cross-cutting focus and also integrated seamless approach for urban applications. And I suppose what we'll have other lectures about urban scale modeling, so I'll just touch some key aspects for integrated seamless modeling only, and also moving to some practical applications from research to services. First of all, about WMO. These years are very important for World Meteorological Organization, because we are now under reform and more focusing on needs of the society, and in particular sustainable development goals. What you can see 17 goals what are presented from the left and right side, and the new Congress, 18th Congress in June 2019, focused WMO to these requirements of the society, and more focusing on sustainable development and disaster risk reduction and corresponding mitigation adaptation to global change. And the main idea is to focus on Earth system science-oriented structure and frontiers of science in advanced fundamental science, in observing Earth system in complex simulations, and combining with exploitation of cutting-edge technologies, satellites, supercomputers, innovation approaches, etc. And in Earth system prediction, seamless approach across time and spatial scales, across topics and communities, to Earth system prediction address the interests and needs of users, first of all, and the society, as I mentioned. And of course, main directions for the World Meteorological Organization as United Nations specialized agencies is doing from science to services. So first of all, we have to provide scientific platform for practical realization. And first of all, as you can see now, one of the hot topic, it's our response to global warming and also disaster risk reduction for natural disasters. And here you can see the main societal challenges, and you can see what urbanization is one of the first topics, and also high impact weather, water and aerosols interactions, and new technologies, and greenhouse gas information system. So these challenges required definitely needs to go into the seamless predictions within the Earth system, because elements of the systems interact and separate consideration is not helping much. So the first part where we will focus on seamless approach and online coupling. Yesterday I already mentioned it, what we consider as seamless predictions or integrated consider several dimensions in this seamless coupling or integration, including, first of all, time scales and spatial scales from street and to global scale, and also integration of processes, physical, chemical, biological, and also social. This is also important. And of course, Earth system components, atmosphere, hydrosphere, lithosphere, pedosphere, ecosystems, and biosphere. And of course, different type of observations and modeling tools, and finally linking to health and social consequences for impact assessments and services and end users. Just returning to global view and theoretical achievements of Professor Zelizinkiewicz. He actually one of the first stressed to consider interaction between these Earth system elements and spheres. And here it's, I just borrowed his slide where interaction of the atmosphere with anthroposphere, hydrosphere, cryosphere, and lithosphere is doing actually within the planetary boundary layer, and this understanding of processes within the boundary layer is extremely important for understanding of this mechanism, because 90% of biosphere and entire anthroposphere interactions include this planetary boundary layer. And Zelizinkiewicz discovered fully orthodox nature and of stratified environmental turbulence, namely of its control by two coexisting arrows from well-known chaos out of order, and yet missed, but now it's a new type of turbulence, order out of chaos, and launching long-waiting scientific revolutions within the planetary boundary layer research. And this fundamental work of Professor Zelizinkiewicz now allows us to effectively resisting to the global pollution and climate change. So this really very important contribution of his science to Earth system modeling community, especially for planetary boundary layers. And here just one example how they are interacting and within the Earth system. One example of radiation, and for example, if we do not consider all chains of these interactions here, for example, if just cut off impact of aerosols on radiation, we will not be able to produce this chain of processes, because the system is really strongly dependent on processes specifically between clouds, aerosols, radiation, vegetation, and also, for example, deposition, snow, and impact on radiation. So this leads to needs to consider integrated approach also for chemistry and atmospheric dynamic modeling. Why the stress moving to online coupled chemistry meteorology modeling? First of all, physical and chemical weather depends, as I mentioned it, of different meteorological processes and particular precipitation, thunderstorms, radiation clouds, fog formation and visibility, and of course, again, planetary boundary layer structure. Its impact on atmospheric concentrations of chemical compounds, especially for aerosols. And from other side, meteorological data assimilation, in particular assimilation of radiative properties, also depend on chemical composition. And also, of course, as yesterday we discussed, air quality forecast also lose accuracy when chemical transport models are running offline without coupling with meteorology. And for climate modeling, it's not necessary to say what integrated Earth system approach is absolutely necessary to understand how the climate system is developing. And large uncertainties, especially for short-lived climate forces, for water vapor feedbacks, are extremely important for coupling modeling. And here it's required new generation of seamless integrated meteorology chemistry modeling systems. And here you can see the difference. What was the difference between online and offline approach? When offline models are running, we run first meteorological model or numerical weather prediction model, and meteorological fields are just reading by chemical transport models each 3 hours or 1 hour, but no any feedback from for example, aerosols to meteorology. For online coupling, all equations for meteorological dynamic and for atmospheric chemical transport models are solved together on each numerical times step, and it's provide first of all correct consideration of interactions, and also provide two-way feedbacks of meteorology and chemistry, what was missing in offline. Of course, there are several types of online modeling also, and we can consider at least 2 types of coupling of chemical transport models and meteorological models. First is what we call it online access models, when coupled meteorology model with air quality models within with 2 separate systems, but just exchange of information on every time step between the models. And this is a suitable way, but the problem is what online access models do not provide consistency, and especially if a numerical grid is different in chemical transport models and meteorological models, or if numerical schemes are also considered for example, transport equations differently. And also for more advanced models, it is used online integrated, fully online integrated models, when, as I mentioned, all equations are solving together. In this case, you can consider full feedback mechanisms and keep consistency and mass conservation. And that's nice to say what one of the first online couplet models start to be developed in Soviet Union, in Novosibirsk Scientific School of academician Marchuk in 80s, and also in US, actually at the same time or even later, such models start to be developed, and now many models are developed. And in Europe also, it is one of the main direction of development of integrated models, and in one of our overview for European models, we analyze and you can find it. And here just one example of running WRF versus WRF Chem with fully online couplet, how to provide downward shortwave radiation fluxes, and you can see here what including coupling and feedback mechanisms substantially improve the modeling capacity and provide really much closer to this. You can see a red line and black dot line for observation. And here just some history of online couplet modeling. Here, as I mentioned, what it started in 1990s and actively developed in Soviet school and also in many others groups. And I will not go into details, but who is interested, you can take a look later on this slide. And what kind of feedbacks we have to consider? Of course, it's clear what meteorology and climate effects on gases and aerosols, and because first of all, meteorology is responsible for atmospheric transport and diffusion of pollutants, but also changes in temperature, humidity, and precipitation directly affect species concentrations. And cooling of the stratosphere due to accumulation of greenhouse gases affects lifetimes, and changes in tropospheric vertical temperature structure, and actually also changes in vegetation. Probably yesterday already in some lectures it was mentioned, impact on dry deposition and emission rates of biogenic species. And also climate change alter biological sources and things of radioactively active species. First of all, aerosols also. And from other side, gases and aerosols also effect on meteorology and climate, or we call feedbacks mechanisms. And we can consider several mechanisms. First of all, direct effects via interaction of aerosols with radiation, decrease downward solar and thermal radiation, and also effect on photolysis. It's called direct effect. And from other side, again, returning to importance of planetary boundary layer meteorology, its affects decreasing near surface air temperature and wind speed and cloud cover, and increasing humidity and also atmospheric stability, what is called semi-direct effect. And actually semi-direct effects considered differently in different schools, and it's quite broad spectrum of mechanisms. And here you can see a demonstration on picture in the left down corner, how semi-direct effects worked with interaction with aerosol particles within clouds. And other type of actually main effects are TWOMI and first indirect effects aerosol surface, cloud condensation nuclei or ice nuclei also within negative temperatures, and reduce drop size and increase drop numbers, and effectively also affecting optical depths of low-level clouds. And on the middle picture, you can see how it works when more particles are within the clouds, and they serve as cloud condensation nuclei. And second indirect effect, aerosols increase liquid water content and fractional cloudness, and also lifetime of low-level clouds, and correspondingly suppress precipitation. So, and on the right corner, you can see a mechanism of second indirect effects. And second indirect effects actually suppress precipitation, and within polluted areas, precipitation can be reduced or at least delayed. This just part of mechanism, and such a mechanism could be considered. Here you can see more detailed classification of effects of meteorology to chemistry, and you can find in our papers here. I don't have time to go into details, of course, here. And from other side, effects of chemistry and aerosols on meteorology. Here also details and what kind of variables in model we need to accurately simulate such effects. But about accuracy, I'll say a bit later. We have many questions which are not solved in models nowadays. And new generation of scientists, I think, will put more efforts in this direction and improve our models. And here, just an example, yesterday I also showed this slide. I just would like to stress now the lowest part about change, and in particular, how aerosols affect radiation, and radiation affect photolysis rates, and photolysis rates, of course, affects chemical transformation and providing new chemical compounds, and also aerosols. So it's a kind of chain of interaction. And from other side, temperature gradient affect turbulence within the boundary layer and affecting surface concentration, and modified boundary layer outflow and inflow and vertical structure. And it could, for example, affect on example of dust storms, impact on intensity of dusting. I'll show some example how it works. So this going to advantages and disadvantages of online models and versus offline. Of course, I'm not saying of for all studies we need to couple fully online. In some applications, of course, offline models are also suitable, especially when we need to consider different scenarios and with the same meteorological fields it could be done faster. But the main advantages of online models are, first of all, meteorological fields accessible at every time steps, and single also executable, and single simulation, single parallelization of processes, and also consistent treatment of processes acting on chemical and meteorological variables, and computed only once in one code. This is very important, as I thought, for accuracy, and also for possibility to consider interaction between chemistry and meteorology, as we discussed previously, and also for data simulation. It's also important to consider effects at the same time scale for chemical and meteorological variables. And of course, big advantage with no meteorological pre-processing, no need to reading meteor files from disk or from to data exchange, because this data treatment sometimes take more than 80% of computation time for modeling within, for example, offline or online access models. So this, I just would like to stress a big advantage of a fully online integrated modeling approach. But there are also some challenges. First of all, chemistry have to be solved at the same high resolution as meteorology. And also, you know what, chemical reactions, some chemical reactions are very fast, and you have inside increase time step, and with to solve such equations. So this, of course, one of challenge, but it's possible to solve. And meteorology changes when feedbacks are activated, and of course we have to consider on the same time steps and harmonize meteorology and atmospheric chemical transport equation. Significant investment to ensure consistent treatment of processes and radiation and transport, and also important to use the same numerical schemes for advection equations, for example. And of course, development of chemistry and meteorology parts not separated, and therefore strong coordination is needed. For example, one of most advanced models developed by US Environmental Protection Agency, or CMARC, is using online access approach, and it is very difficult to for them now to move to online coupling, because models are already formed separately. And if to build fully online coupling, you need to rewrite full code, which is huge and prepared during several decades. So this challenge when ready models start to couple it with meteorological models. This is the reason why WRF-Chem is very successful, because it was started this integration practically simultaneously. And George Grell, who led this work, started working from the beginning with the development of WRF and Chem. And for European efforts, we have a special cost action for a framework for online integrated air quality and meteorology modeling, EUMET-CHEM, and analyze. And you can see here a number of European models, and now we analyzed 18 online couplet models, but it was actually more than 5 years ago, and nowadays the number of models even longer. And here, for example, in This document, what yesterday I demonstrate what is Yanjan, we prepared WMO best practice of modeling of atmospheric chemical weather. Here you can see main online, fully online couplet models worldwide, and you can choose if you are willing for your research or for your applications to use, because most of models actually are open access, and you can use it. And of course, CosmoArt is one of most used by Russian Hydromet model, and WorldChem is actively used. And EnviroHelium, of course, because we are coordinated development of this model with international community, and I suppose Alexander Mahura will say much more about EnviroHelium model. And of course, you are very welcome to use this model. And now also it's coupled with a new Harmony meteorological core. And just about effectiveness of integrated modeling approach. You know, European Center for Medium Weather, Medium Range Weather Forecast move to also integrated approach, and now Copernicus Air Quality Service, for example, using this CIFS fully online integrated model. But in the beginning, they start also from coupling with this data exchange between IFS, meteorological global model, and chemical transport model. And we discussed a lot with Johannes Fleming, who was leading this work. And of course, it took time, but when they agreed what online coupling is much more efficient, and they move to fully online CIFS model instead of previous Mozart TM5 IFS couplet system. And he says what the fully online couplet models, which was developed in the MARC project and now used in CAMS, Copernicus Atmospheric Service system. It's 10 times more efficient than the couplet system previously used. So this just example of a big advantage of fully integrated systems. And EnviroHelium model, what I already mentioned it, also was completely online couplet strategy used, and physics is considering simultaneously meteorological processes, turbulence schemes, radiations, surface schemes, and also this interaction of aerosols and gas phase chemistry. And of course, also considering boundary preprocessor and data simulation. I suppose what Alexander Mahura will, on practical exercises, say more about specific. And also some advantages of online coupling are demonstrated here. For example, it is just demonstrating improvements due to indirect effects. And at least for precipitation amount, fully coupled models with including of indirect effects and aerosol cloud interactions improved forecast of precipitation by EnviroHelium versus simple Helium without this coupling. Another example, what was done by Kong and co-authors using WorldChem for Moscow forest fires in 2010, and also it was quite interesting case for analysis of feedbacks of aerosols. But that time, unfortunately, it was no big cloud, so mostly it was direct effects. But direct effects improved, for example, normalized mean bias significantly reduced by 10–20% for PM10 when included aerosol direct effects. Of course, indirect effects were not much visible there because no clouds and precipitation that time. But also effects on reduction of boundary layer height was quite significant, and it was demonstration of importance of PBL schemes and resolving of boundary layer turbulence. And here more example from our experiment for cost action with WRF-Chem also, and you can see how direct and indirect effects changed boundary layer height. If direct feedbacks usually decrease PBL, for example, 80 meters it could be, and especially in summertime, on the right side, you can see direct effects, but when we include both direct and indirect effects, the picture is changing quite dramatically, and also in different directions, indirect effects can change the boundary layer height. So this is just a good demonstration of what for atmospheric turbulence consideration of aerosols and meteorology are very important. Another example, what I would like just to stress with our WIGNI group simulations, and it is done by Samuel Remy from ECMWF. When a dust storm over Egypt was considered with effects, direct effects, and without. And it's quite interesting mechanism. When no direct effects and with including direct effects actually decreasing radiation to surface, and surface is slightly cooling, and it leads to low-level jets with increasing wind velocity due to inhomogeneity of fields. And it leads to increasing of dusting. So practically dust storm and dust particles produce effects on meteorology, and meteorology effect on dust intensity. So it's chain of processes. And of course, such effects is absolutely impossible to produce when you are running offline chemical transport model without full integration in seamless approach. But just returning to my comment about uncertainties. This another example, it was several years ago, 2015, so now models are improved a bit, but just a demonstration what our understanding of indirect effects and mechanisms is not enough. Here is intercomparison between 5 different models. As you can see, with impact of indirect effects, and you can see what results are very different, and sometimes impact in different directions from model to model. It is not surprising because mechanism of indirect effects in many cases strongly non-linear and in different directions. So one mechanism is moving and balance between different mechanisms is extremely important. And of course, it's very sensitive to parameterizations which are used. So this a nice example of also importance of future development, and also for new scientists and for students to put your efforts for improvement of models. So this, just to conclude, I would like to say what kind of improvements we can reach with online coupling, not only for air quality forecasting, what yesterday we discussed, but also for meteorological, for numerical weather prediction, and for climate and Earth system modeling. First of all, a relative importance on online integration and level of details necessary for representing different processes and feedbacks can greatly vary for different communities and for different applications. For example, for numerical weather prediction, may not depend on detailed chemical processes, but considering clouds and radiative effects on aerosols can be important. For example, for fog and visibility and precipitation forecasting, for surface temperature, etc. So, and for climate modeling, also, for example, feedback for greenhouse gases and aerosols became extremely important. However, in many cases, long-lived greenhouse gases on global are not fully online integrated chemistry, and full-scale chemistry is not critically needed. Still, it is too expensive. But from other side, for short-lived climate forces, online coupling is necessary for climate modeling. And in the last IPCC report, what was published 1 month ago, it was clearly stated importance of these mechanisms, especially for aerosols. And for chemical weather forecasting, as yesterday also we taught, and prediction of atmospheric composition, online integrated definitely improve air quality and chemical atmospheric composition projections. And also just would like to stress the main gaps. First of all, understanding of several processes, aerosol cloud interactions are poorly represented, and also data simulation in online models is still to be developed, and also model evaluation for online models need more process data and long-term measurements effects. Well, I think I will not jump to the urban applications because you have a special lecture for that, but in my slides are included following, and if someone interested can consider in details. Just would like to stress what for urban application, this seamless approach is even more important, because urban processes are formed not only on local scale, but also interaction of different scales, time scale and spatial scales, first of all. And from other side, for urban areas, we need to build a kind of integrated systems and integrated services for weather, urban climate, urban hydrology, and urban environment. And these processes, as we demonstrated on global and regional scale, are extremely interacting, and of course they should be also considered together in coupled and in seamless approach. Thank you very much for your attention. And